Hi, welcome to session 3 of module 1 of the course Data Science for Engineers offered by the Department of AI and DS. So in this session we would be talking about different distance measures that is used in the field of machine learning. Let me give you an overview about what do you mean by a distance measure. So here you can see two different cluster of points, that is a group of points. The first group is annotated as omega I and the second group is annotated as omega j. And you are having a new visitor here, a new point x. Let's call that as a reference point x. Now if I ask you what is the most likely cluster to which this new point would belong to, just by eyeballing you might tell me that okay, it belongs to the cluster or the group omega I and not in omega j. So here the distance that you have used just by eyeballing, the distance that you have used is the classical Euclidean distance, that is the straight line distance. So you might have taken the nearest point to x from omega I and the nearest point to x from omega j, and out of that which distance is the shortest, you would be picking up that point or that cluster to be the cluster to which x would belong to. And here, yeah, omega I is very near to x than omega j, but this is always not the case. It's not always that straightforward. Like for this example, here you have again omega I and omega j, and you have the reference point x, and here it's not very clear whether the nearest point from x is in omega I or omega j. It could be even in omega j, but from eyeballing we can sense that the pattern in which the data is shown here, the way in which the data is distributed here, it is more likely to be in omega I. But here we cannot go for simple straight line distance. So that is the entire motivation for having distance measures, because we cannot always go for the straight line distance. For different types of data we need more complex distance measures. And distance measure is also called as similarity measure or proximity measure. That is also another name for distance measure. So what do you mean by proximity measure? So it is the inverse of distance measure. So if a point is very far from another point, we can tell that their proximity measure is very less. The distance is high, then the proximity between those 2 points is very less. But if the proximity between 2 points A and B is very high, it means that the distance or the distance between those 2 points is very less. If the proximity is high, then the distance is very less, which means that the 2 points are very near to each other. Okay. So having this introduction, now we can jump towards few of the classical distance measures. So we will see 3 distance measures in this session, and we will see some advanced distance measures in the session 4, in the next session. So to begin with, let's see what is a Euclidean distance. It's also called as L2 norm, and you can see here the equation given for Euclidean distance between any 2 points x and y in the real plane. So d of x comma y is equal to square root of sigma I goes from 1 to n xi minus yi all square. So this is a very famous equation. You might have seen this from your high school days onwards. You can derive it very easily by using Pythagoras theorem. And let's see an example here. You have 2 points x and y. The x-axis of x is 7, the y-axis of x is 3, and the z-axis, the z-axis of x is 5. Same for y, the x-axis is 3, y-axis is 2, and c or z-axis is 6. And the Euclidean distance can be measured as square root of 7 minus 3 whole square plus 3 minus 2 whole square plus 5 minus 6 whole square, which would be equal to square root of 18, approximately equal to 2.4. Okay, so we are just substituting this points into that equation. Right, now let us go for a bit more different distance measure called the Manhattan distance measure. Manhattan distance measure or L1 norm. So like L2 norm for Euclidean distance, we have L1 norm for Manhattan distance, and this distance is expressed by Manhattan distances of x and y is equal to sigma of I equal to 1 to n xi minus yi and its absolute value. So the absolute value of xi minus yi. We will see an example just to make it more clear. And remember that it is also called taxi cab metric or city block metric. So if you take x and y, so let's say x is 7, 3, 5 and point y is 3, 2, 6, the same values as before. So these are two 3D points. The Manhattan distance would be absolute value of 7 minus 3 plus absolute value of 3 minus 2 plus absolute value of 5 minus 6, which would be equal to 6. Now instead of 735, instead of decimal numbers, what if we have binary numbers, right? So in that case it's like asking, you have got binary number x and binary number y. Okay, maybe like 4 digit or 8 digit or 16 digit, whatever it is, you have got two numbers x and y which are binary numbers, and if you use Manhattan distance to find out the distance between them, then it is famously called as Hamming distance. Okay, and there is also a very neat story behind Manhattan distance. So you can see that name Manhattan or taxi cab. So briefly, this is how the story goes. So when a new person, a stranger comes to the city of Manhattan, the city drivers, the cab drivers there, taxi cab drivers there, they're a bit greedy, and because of that, they'll try to make the person go through the most long distances possible, so that they can bill them more dollars. Okay. So what they'll do, instead of going from straight from A to B, they would be going through the x-axis. That is what 7 minus 3 denotes. You complete the difference between the x-axis of that point. So you may travel from the value 7 of x-axis to value 3, and then you will complete your y-axis. That is from 3 you will go to 2, and then from 5, that is a z-axis, from 5 you will go to 6. So you will take 3 90-degree turns or multiple 90-degree turns just to reach your destination. Instead of just going the straight line distance, you will take multiple 90-degree turns, so that the cab will travel more distance, and you can rip off more money from the customer. Okay, so just remember that, the motivation behind that name. Now let's go for the third distance measure in this session. So the third distance measure is called Chebyshev distance measure, which comes after the famous Russian mathematician called Chebyshev. And the distance metric for Chebyshev for the distance between 2 points x and y is equal to the maximum of the absolute value of xi minus yi. Right. So you may not clearly be able to find out a scenario where this could be useful, but it is useful in space explorations and all. Sometimes these kind of measures people use. So just to give you a review about how this works, let's take these 2 points 7, 3, 5 and 3, 2, 6 and see the Manhattan distance here. Manhattan is 6, we calculated before, but what is Chebyshev here? We take the maximum of either 7 minus 3 or 3 minus 2. We take maximum out of these three values. 7 minus 3 you get 4, and 3 minus 2 minus 2, the modulus of that, the absolute value of that is 1, and the absolute value of 5 minus 6 is also 1. So you have 4 here, you have 1 in the second dimension, and you have 1 in the third dimension. So max of 4 comma 1 comma 1, which is 4. Right. So you can get an idea about like how this is. So if you have the generic case, if you have 10 different dimensions, then you have to find out the absolute value of the difference between each of these dimension, and then take the maximum out of that. So that is how Chebyshev distance is being calculated. And there are a lot of motivations in using this kind of distance measures. So one example I can tell you is, just think about a use case from space expedition, where so I'll just give you a preview about that, not the exact nuanced details, but you an idea, and you can build it up from your creativity, like how it could be Chebyshev distance. So let's say there is 2 aircrafts, not aircrafts, it is spacecraft, which is outside from the gravitational force of Earth. It is in the atmosphere. 2 spacecraft that is starting from point A. So it's a 3-dimensional point. They are starting from point A. So after going some X amount of distance. So let's say the first aircraft moves from that point, and after traveling X kilometers or something, the next aircraft also starts. Okay, so it goes through some distance like that. Both of them are having the same, the same velocity, let's assume, and it goes through the x-axis for some time, right? And then suddenly it takes a turn to the y-axis. Again, the same thing happens. Both of them stops before the turn, and the first aircraft will go for x amount of, for a y amount of distance, and then the second aircraft starts. And then for the z dimension, let's say it stops after traveling some distance, and it reaches the a point, let's say point C, and the first aircraft starts again its journey through the z axis or z axis, travels c distance, and then the second aircraft also moves along. Just think about a scenario like that, right? So through the y-axis, both of them started after the first spacecraft moved x distance, and if you think about the y-axis, both aircraft started going after the first one moved y distance, and for the third case, it happened after z distance. So you have 3 values, x, y, z. Now here, if I ask you like what would be the length of the cable, optimal length of the cable that should connect between these two different spacecraft, it would be the maximum of x comma y comma z, assuming that the cable that we are connecting is non-stretchable. I don't like no tricks there. It's a non-stretchable. It's not elastic. It's a usual like a fiber optic cable or something. But yeah, it is flexible, but it's not stretchable. So if you think about, if you cover all those boundary cases, right, then you will understand that the maximum of x comma y comma z, that much is required for them to travel together. Okay, so just think about that, why it would be like that. I'm just giving a motivation for Chebyshev. So like that, you can also think about the second distance measure, that is Manhattan distance measure, where it could be useful. You can try to find out a scenario in which the distance between 2 points could be calculated by using Manhattan distance, and that would be the right distance measure to be used in that scenario. Okay, so that's all from this session. So in the next session, we will start with few more advanced distance measure that is used in the field of data science. Thank you.